So I was watching Christoph fumble and try to get his laptop working with the display today, and I've come to the conclusion that this is pretty much equivalent to storage technology as it stands today. Here's your NVMe adapter. There's IDE, SAS, and SATA drives connected on the other end. Anyway, so this talk is going to be about a product that we've been working on for a few years and just started shipping in the past year for essentially composing large clusters, large Linux clusters for scale-out applications. I'm going to race through the slides. There's a lot of material that you can look at afterwards. I'm not going to talk about quite a bit of it, but I encourage you to follow some of the links and some of the information in here. Okay. So I want to give a quick definition of what composable infrastructure is, what the administrator sees. What we're trying to do is basically simplify deploying large clusters for big data applications like Hadoop, NoSQL databases. These range in the hundreds of compute servers with lots of storage attached to them. They're very data-full deployments. I'm actually not going to talk about technology trends. I've moved out to the background. Suffice it to say that there's the emergence of low latency, high performance, high bandwidth Ethernet has basically been taken advantage of for big data applications and scale out architectures for applications. And this has become ubiquitous in certain parts of the data center. And we're providing an orchestration solution to manage that hardware sprawl. I'm going to touch on some future directions and then recap. So what is composable infrastructure? It's the technique of basically taking captive DAS deployments, disk with compute, and breaking it into its components of storage and CPU, and have thin composable clients with storage boxes that you basically construct as right-sized servers on the fly, depending on your applications. There are a lot of big data NoSQL applications that are designed to be scale out today. The important thing about all these applications is probably two things for this talk. One, they all work or are designed to work over Ethernet fabrics, commodity hardware. And the second thing is that each one has a reference architecture about the amount of storage to compute that works for that particular application and whether the storage should be spinning disk or flash. Nothing is the same. So they're all different reference architectures for deployment. The confusion to me around composable architecture, composable infrastructure comes from everybody's definition of it. Many people are positioning composable infrastructure solutions for basically to provide a blade chassis management system, storage blades and compute blades, and the thing about this wide, that'd be a rack, and being able to attach storage flexibly to the compute. 10 servers, hundreds of drives in a rack chassis. Not of interest to us. That is not the target market we're playing into. We are actually looking at 10,000 servers, 100,000 drives. We have several customers. Our biggest production deployment is about 1,000, 2,000 servers and near 10,000 drives deployed over a couple of data centers. Let me go forward here. So just a quick animation, and then we'll get into the issues we're seeing and what are the problems we're trying to solve defining a composable infrastructure product. Basically, you've broken down the components and you have compute and storage, varieties of storage. They might be tiers of storage that you've broken out into, say, slow, fat drives, 3.5-inch, flash drives, SSDs, and you might have faster drives for certain applications. Recognize that a lot of these big data applications, they incorporate their own storage stack and an IO stack above the Linux kernel and Linux file systems and manage it on their own. They take responsibility for all of their application, recovery. It's all application specific, and again, varies from application to application. For the applications that are reading and writing sequential I/O, spinning disk is perfectly fine because they never do random I/O. For the NoSQL application, some things like Aerospike and stuff, they want SSDs because they're using the flash devices as backup for an in-memory database and high-speed, scalable transaction processing system. So you see a panoply of applications on the right. Essentially what our solution allows you to do is to grab some compute, grab some storage, and create a closed, secure cluster for running that application. Here we have a Hadoop instance running on spinning disk. Maybe you want to deploy a Cassandra instance running on spinning disk, or you're going for something more high performance, which would be an Aerospike instance running on flash. Again, the ratio of storage to compute varies. You could have one compute node with 4 spinning drives and have 100 nodes for a Hadoop deployment easily. For Aerospike, there are deployments I've been seeing are at one dual socket node with 12 to 24 SSDs and deploying up to recently only 100 nodes for a millions of transactions per second deployment, but they've increased that at customer request to go up to 500 nodes for larger scale out. Again, performance and capacity to scale out applications is achieved by horizontally scaling out, and you want to flexibly add compute and storage as your application needs grow. So the best thing I could come up with like the 13-word definition of composable infrastructure is think bare metal virtualized infrastructure for Linux at scale without the VMs. The one thing about these applications is that they're running on bare metal in their reference architecture deployments. They are adopting deployments on top of containers because that doesn't actually interfere with their performance, but they're definitely not being laid out on VMs like VMware or KVM at production scale, except in test instances. So what's the problem that we had to solve when we basically tried to manage at scale multiple applications, hundreds of nodes, thousands of nodes, and thousands to tens of thousands of disks? I got my disaggregated storage in my pocket. So here's my NVMe drive. So right, that's simple. I can basically disaggregate storage, whatever, right? It's putting it back together again in a reliable, durable way at scale that it basically persists spread out over a network that by definition from the commodity components of the compute and storage and the interconnects over Ethernet can be subject to partitions, failures, and essentially if you're running 10,000 servers, 100,000 disks, you have to consider that you are always in degraded mode. You will always have a disk failure. At much smaller size, you'll be dealing with a couple to 3 disk failures a week, and you'll have to manage that, and your applications are designed to work around it and continue past it. That's all in the design of the applications above. However, managing the physical infrastructure and actually going into a data center of thousands of nodes and replacing components, replacing disks, is a rather tiresome chore. So we're trying to basically provide you the way to virtualize that, squint your eyes, and essentially managing it through software orchestration. The challenges are essentially creating secure, durable bindings between servers and drives. I'm going to talk about some of the pieces in the network that are used to glue the parts together. But in the end, the only thing we care about is the server and the disks associated with that server, and then basically cookie cutter to as many nodes as you need with storage. The problems for the Linux stack is just lots of nitty details about, for each application, again, it's multiple protocols. So some applications are going to be running over NVME now, over Rocky v2, or coming up NVMe over TCP, right? But widely available with commodity hardware is iSCSI running out of the Linux kernel. Because we want to have availability to the combined storage nodes when we're aggregating storage, we are using the multipathing capabilities of Linux on the servers. The file systems are, again, defined by the application, not by your preferred file system. It's the reference architecture from the ISV. Some we want RAID configurations. And here's an important thing. We don't do any really data management in the storage. We're essentially replacing the captive DAS deployment reference architecture for these applications. And that means storage that was in a white box with a compute motherboard. And that was basically, there's 100 of them. We are separating out that direct attached storage, that DAS, from the box and putting on the network. We have to look like DAS. We are not doing any RAID in the back end. We're not doing anything actually at all interesting, per se, from the perspective of things like an enterprise storage array. All of the data management and the availability, the recovery is being done on an application by application basis, and they don't want that done in the back end. Again, different hardware vendors and different storage interconnect technologies, and we're also providing capabilities for encryption for data in-flight and at rest for essentially GDPR considerations that all of our customers are now talking to us about. So once you have a deployment, you have the problem of upgrades at scale throughout your network. And that upgrades throughout your network might be dependent on application requirements. So we have the need to support rolling upgrades where you're basically replacing compute at a different rate than your storage. You have to have multi-version support in the management framework and be able to run, if you have a 100 node deployment, you're going to replace 10 nodes at a time on a platform upgrade of the compute. You need to basically run through the multi-versions of the hardware and the software running on the platform. And then being able to replace failed data path components. One common operation you will do continually is essentially expand your cluster to provide more performance is the likely thing you're going to pull off. And you want to do that when you're running your application. You want to add compute nodes and storage to your cluster without disrupting the running application. You just simply want to add capacity and performance. When you lay things out over Ethernet, you are going to run into partitions, so all of your components for the management have to be resilient to network partitions and failures, and you have to be able to, when you're managing the configuration, have your platform retry configurations if something happens during a push of a configuration. So it's all about managing and automating complexity at scale. So this is about all I'm going to do about the GUI. There is a demo online. Follow the link if you want and you're interested. If you're a new user doing a proof of concept for a platform and you're doing a test setup, you're probably going to be using our GUI. You get a view of the inventory that is under control for the Drivescale Composer platform. You will have a little panel that allows you to spin up as many nodes and storage as you have under control of the platform. So over here, I'm spinning up an XFS file system across a couple servers. This is a test instance. You create a cluster, it spins it up, comes back in a couple seconds or less, and you have a cluster ready to run your application. And so let me just stop here. You don't really need to know anything about the configuration that underlies your application, though you can go in and specify things. You don't have to specify transports. That's just basically going to try to every path it can set up. So if your storage systems are capable that are being shared, your storage systems are being shared with your across many application clusters. Parts of them are being vended out. And the disks are not shared, but the storage interconnects are shared. That you may have some applications running NVMe over Fabric. You may have some applications running iSCSI, which is widely available and commodity. But you don't have to care. The way our platform works in plumbing the stack from the application to the storage endpoints is to try to do the best it can from the perspective of performance and plumb whatever it can to to achieve the highest performance interconnects. When you watch the demo, if you go up there, you'll notice Chris, the guy who did a lot of the design of the product, you'll watch Chris look puzzled at some point during a switch of the storage to a new set of compute blades. He kind of crinkles his brow. He had forgotten he had actually had NVMe over Rocky V2 enabled on the storage components, and he inadvertently connected it to a bunch of Rocky V2 enabled compute clusters. It all worked. He just kind of went, oh, that's Rocky V2. He wanted to do just a simple iSCSI demo. It was a transparent binding. When you create clusters, they appear in logical clusters, are basically equivalent to a single application deployment, and you'll have one or more clusters, likely many. If all you're doing is deploying a single Hadoop instance of 100 nodes and you're not looking at anything else, you don't need our platform. You're not managing multiple applications, and it's fairly simple and straightforward. But I've still yet to meet a customer who has Hadoop that doesn't have the other applications too, or is bringing them on. So the important phrases, there's a little glossary here, just so, because everybody disagrees on these terms. Disaggregation, breaking up compute and storage into discrete elements on an Ethernet network. There are people who are doing different levels of disaggregation or using things like InfiniBand interconnects and stuff. Completely uninterested in that. What we're interested in is the commodity deployments for these scale-out applications that are all running over Ethernet. So not really interested in the other interconnects. Composition, basically secure binding of servers to drives. A logical cluster to us is a secure, closed, non-overlapping set of durable server and drive bindings used to host a single application. When you create a cluster for Hadoop, you're not running it in in VMs that are being shared with other applications on that host. The applications are being designed by the application providers to use all the capabilities of the host you deploy, and you add enough storage such that that application runs well. So it's not multi-application hosting, but you are hosting multiple clusters for different applications. The other two concepts I just want to mention before we dive in a little bit more is key to our Composer platform, our orchestration platform, is a concept that everything that exists under management is called the inventory of compute and storage. The configured clusters that are not the free pool are known as configurations. These are things that are under management and assigned to an application. You create a logical cluster configuration from a set of available nodes. Once you allocate it, they are allocated and not available for use by anybody else. So I touched on this in an earlier slide. Yeah, just a small composable thing. One of the things, what we're trying to do from an economic perspective is that when you're deploying an application for the first time, the status quo is to buy rather disk-full systems, 8, 12, 24 disks or SSDs in a compute box. So frankly, those units are much lower volume than smaller compute blades being used by the hyperscalers. These disk-full configurations from multiple different vendors are more expensive. And once you do the purchase time acquisition of a single configuration, you are pretty much locked into 8 disks at max per compute node. So if you break it up, you can essentially mix and match however much storage you want with however much compute you want. Again, the design goals, scalable, durable, highly available, correct, and performant. I do have some benchmark information towards the end. So this is the pieces of our system. The big part for us is the Drivescale Composer platform. This is a triple replica management platform that essentially runs the configurations and drives the configurations of the network. You're either going to create clusters for your application with the GUI, which we think that a lot of new users would use, or if you're like our oldest customer, you'll be using the APIs to script application clusters with a little bit more customization than you would get from the GUI, though the GUI does allow you to define templates to customize all of the moving parts of the application. The platform is triply replicated, running in outside of the application clusters. On each compute server and storage component is an agent running in user level. The agents act on configuration asks from the manager to affect the change and create the bindings of compute to storage. I have a lot more information on that later on. The important thing, I put a little asterisk to remind me about this. Important thing about the storage adapter agents, nobody connects, this disk is not sitting there idly in your data center. 5 minutes to go. Holy shit. Okay, Jesus, fuck. Okay, it's not sitting there idly. It's essentially aggregated behind a controller. The engine is using two components, the Zookeeper and MongoDB database. The Zookeeper, boy, I'm way out of time. The Zookeeper database is essentially providing the durable bindings and atomic write capabilities to maintain the integrity and correctness of our configuration pushes. It's a durable configuration store, and it's the important part I wanted to touch on today. When you install Drivescale, you do the installation, you just install the user level agents on the storage and compute. You fire everything up, and the first thing they do is auto-discover all of the available storage and the properties of the compute nodes and register them with the Composer platform. During operation, you're simply creating clusters out of the available inventory to define secure, logical clusters. The Zookeeper framework reinforced and influenced the product design. We have this model of essentially, since it's a distributed system on Ethernet and things can fail, we have a model of a configuration that's the one true version of what the world should be. And that configuration is the current state. When you make a modification to create a new cluster, you define a desired state where you are affecting multiple components, the compute nodes and the storage connected to the server agents out on the network. The key point for our architecture is that the Composer expresses that as a set of, this is what I want the world to look like. I want these drives attached to these compute nodes. And it breaks it down into problems and farms out the work to the servers and the storage adapters themselves. The Composer doesn't actually pipe or plumb the Linux kernel to the storage devices. The adapters and the servers themselves act upon the configuration change and will keep retrying to achieve the desired state. We go over here a little bit. This kind of design led us to a certain layout of, like during discovery, the inventory is driven by the agents out on the nodes. We don't go scanning the network from a central location looking for information. The agents are actually responsible for creating the inventory. The Composer is actually writing the configuration information out atomically such that it is durable and recoverable. If it goes down if we crash in the middle of trying to propagate a configuration out to the network, which is basically the agents are watching for configuration changes for the parts of the problem they own, it comes back up and recovers, and the agents will pick up where they left off and continue the operation. So we break this problem up in this way because we really need to not have a single point of failure or an overwhelming problem for the management platform to actually try to plumb remote server and storage. You can look at this later on. I tried to give you kind of a data design of how we break up of the information that's important from the server inventory and the storage adapter and drive inventory. and reporting status back from the storage and server components. This is the stuff below the line over here in our kind of key value store. The configuration is essentially this moving of a current state, what's allocated, well, basically you're going to create something, commonly create a logical cluster out of available components, and you want to achieve a desired state of server storage bindings. That will basically produce a move of inventory into allocated cluster design in a distributed fashion. The steps are kind of down here. I apologize, I am really out of time. I am out of time. Anything important here? Right, so this is all sort of dependent on atomic writes being done of the cluster configurations to allow for recoverability. The cluster is broken up into the component parts for each of the servers and storage adapters, which triggers the distributed configuration change from a current state to a new state. So we have the truth of what a logical cluster is, and we have a derived truth that is recoverable in the event of crashes and failures that is derived from a logical cluster master definition. And this is the distributed management of the storage and the compute. That's the definition of a logical cluster as a JSON representation out of our Zookeeper database. And again, the important thing on the storage agents and the servers, they derive their configuration from the configuration that the composer defines and will retry forever to essentially achieve the configuration that you want. There is a little bit of a logic flow here for what the loop would be on the server adapter in terms of if I'm removing disks, replacing disks. The important thing in here is that the agents do not disrupt existing server to disk connections that are not affected by the configuration change. Else the application would be entirely unhappy. If you're adding a disk to each node in a cluster, you do not want to bring all the other disks down in order to add the disk because the application will hiccup. Last slide. From a performance perspective, this is a comparison of the Aerospike database benchmark, ACT4. You run it for 24 hours. It's 2/3 read, 1/3 writes, large transfers, but transactional processing reaches steady state within 24 hours. For composable infrastructure, people's biggest worry is that the performance is going to suck compared to direct attached storage. The Rocky V2 and iSCSI results are shown. The thing that we are suffering on over here is latency. Everything else is direct attach on SSDs. The thing we are suffering on is latency, so we have slightly more % of the transactions at a higher latency versus the direct attached storage, but the throughputs are right up there. The HG Ultrastar SN200 is roughly the same as a Micron 9200 Max. Sorry, I'm done. Apologies for the run.
One question.
Yeah. One question? No question?
Maximum one question. If not, thanks.
That's it. Thank you.